Good afternoon. Today I will talk about a framework that we've developed using the AWR and National Instruments software and hardware for developing wireless LAN solutions for 802.11ac. As a brief history of the 802.11 family of standards, they started back in June of '97, which seems a long time from now, with the and then in September '99, the 802.11a and 802.11b were released, followed by GN in 2003 and 2009, and finally in January 2014, the 802.11ac was ratified. The 802.11ac is also known as the very high throughput, or VHT, because it does provide a very high throughput compared to the previous standards. It does operate strictly in the 5 gigahertz band, and it tries to reuse as much as the 802.11n technologies as possible in order to be backwards compatible with the previous standards. And it does also coexist with the 802.11a and n in the 5 gigahertz band. Some of the modes that it provides are the single station throughput, which provides throughputs over 500 megabit per second over an 80 megahertz channel, and also the multi-station throughput, which provides throughputs of 1 gigabit per second over an 80 megahertz channel. And some of the new technologies that are specific to the 802.11ac are the 100 megahertz channel bandwidths, which is the 80 plus 80 megahertz contiguous setup, and something that's novel is the 80 plus 80 megahertz channel bonding, which includes 82 disjoint 80 megahertz channels. The MIMO setup was increased to up to 8 spatial streams. It allows for multi-user MIMO and also higher modulations, which you just heard in the previous presentation. This standard now goes up to 256 QAM. It does actually include standard beamforming techniques and space-time block coding and low-density parity check coding. Some of the new applications that are actually made possible by the 802.11ac are the in-home streaming of HD video to multiple clients, rapid synchronization and backup of large data files, a wireless display where you can actually stream a wireless signal to a high-def monitor. It will allow for backhaul traffic, either in mesh or point-to-point configurations. The deployment of large campus and auditorium setups, as well as manufacturing floor automation. So some of the unique design challenges for 802.11ac devices are more stringent requirements in spectral flatness. As you go to really wide bandwidths like 80 or 100 megahertz channels, the spectral flatness becomes more challenging. And also interference robustness. There is a weather radar band at the 5 gigahertz, and the 802.11ac should be robust to such signals. The contiguous band mode, the 80 plus 80 megahertz, requires either multiple instruments for generation and analysis during development, but that also creates issues with additional synchronization in development or testing of such devices. The higher modulation schemes, as I mentioned, 256 QAM, would require better transmitter constellation error performance, and it will require better receiver input sensitivity. So usually what we do is that we have these three different phases, these main different phases in a product development. We start with design and simulation, and this is done again in simulation. It's the first stage in developing a product, and then once we reach to a certain points, we move on to verification and validation, and finally we move on to manufacturing and test. And in a typical development cycle, during these three different phases, let's say the transmitter IP is first developed in software, and then we have to move into some other platform for prototyping and for verification. And then finally we have to move on to manufacturing test equipment. And every time we move from one phase to another, there is a new learning curve for engineers. There is more risk in terms of having to debug all the inconsistencies between different vendors or different implementations. So what we've done is that we have taken an approach where we try to use the same IP over all these three different cycles, and we've done that by unifying the IP in terms of the transmitter implementations and the receiver implementations, and we've been able to achieve these by reusing the same libraries across these three different phases of the design process. So to do this, we're using several tools, software and hardware tools. And first, we're using the AWR Visual System Simulator, which is a system design tool that is used for it's widely used for designing of wireless solutions. The second one is the Microwave Office, again from AWR, which is a circuit design tool, and it's really it's used for designing the RF components that go into the RF links for such devices.